you have not had calculus, because I know there's at least one of you in here who's avoiding it, there's an omega that pops out.
That's me.
So my formula here for the voltage, we have, well, I got the two negatives. I'll keep it in for right now. Negative BA times negative omega sine omega t. So I get BA omega sine omega t. So I now have a formula for my voltage based upon the area of this, and then all we need to know is time and magnetic field. This also sets up in the fact that as the thing is spinning around, my voltage is oscillating back and forth, and if my voltage oscillates back and forth, my current's oscillating back and forth. And we're now talking about an alternating current. Otherwise known as AC. Questions up to here?
Yes. I don't know, part of this could have been because I came in late, but I'm still just confused conceptually about what is going on here.
All right.
And how it, I guess, apply, like, I don't know, is this kind of a derivation that we're going through, or is this like?
Yeah, it's kind of like a derivation.
Kind of like a derivation, okay.
I believe this formula right here for the EMF is in the back of the chapter.
Okay.
So, Brooke?
Actually, finish answering their questions.
All right, so what we're doing here is imagining I've got some wire around the edge of this. So basically, this is physically, pretend this is physically not here, but I do have a wire along the edge. I have a magnetic field that's running across the room in that direction. And then I'm spinning this. Because magnetic flux is the magnitude of the magnetic field times the magnitude of the area times the cosine of the angle between them. Again, my area vector. Oh, that would have been too nice if that was stuck in there. My area vector is pointing, we determined earlier, we'll just make the area vector pointing in this it's perpendicular to the surface. And we said this direction. If my magnetic field's going that way and my area vector is going that way, we're at maximum magnetic flux. As it turns, magnetic flux is 0. Magnetic flux is the negative of the maximum. Magnetic flux 0, maximum 0, and so forth. My magnetic flux is constantly changing. So therefore, because my magnetic flux is changing, I'm going to have an induced voltage, or EMF. That's all I did was I took my formula for magnetic flux, stuck it in for magnetic flux, which gets us here. And then, since magnetic field and the area vector are constants in this situation, I pull them out. And so, factored them out using the math terminology. And so what I'm left with is the magnitude of those two terms times the change in the cosine over the change in time. And then that's when we went through all this.
Okay. And is this something that, like, is this applicable in real life, or is this just one of those things that makes for a good problem, or where, like how does it, I'm just.
This is the essence of.
Of course it's applicable to real life. Is that even a question?
This is the essence of power generation in our entire country.
Okay, that's what I was wondering. I was wondering where this kind of came in. Okay.
Yeah, thanks to Westinghouse, this is standard in the U.S.
Okay.
Just to clarify, you said because the magnetic flux is changing, we'll have an induced voltage or EMF. Is that the same thing as the motional EMF, or is that something else?
It's all related. That technically is something else. I would say motional EMF would be more apt description if we just had a single bar that's sort of going through the magnetic field, as opposed to an actual circuit.
Right. But motional EMF is an induced voltage.
Yes.
Okay.
You're going to get induced voltage as long as the magnetic flux is changing.
Right. Okay. Thank you.
Yep. Other questions at the moment? Brooke?
Are we going to need to know the sine part? I was following you up in like through the cosine part, and then you switched to sine. What does the sine have to do with?
Because change in cosine over change in time is sine.
Is angular.
Actually, negative sine. Yeah, it's this whole bit right here is the same thing as this.
It's okay. Yeah, that's what I was. Okay, thank you.
And we will come back to revisit this relationship when we, probably next Monday, when we actually derive the speed of light.
Yeah, will we do a problem where we started off with sine and then, like, basically instead of having the delta cosine, we just have delta sine? Is that a possibility, or?
It's a possibility. It would not be my intent. 152, I tend to start the whatever the generator is. I tend to start it at the maximum value, but we could start it at 0. I could have started it like this and then spun it around. So at time is equal to 0, I'm starting at 0, then it becomes positive, 0, negative, and so on. You want to go ahead and do that part now?
Sure, why not?
Okay. Well, actually, we'll come back to the omega. We'll leave that out for the moment. Let's just start out with a normal cosine curve. Keeps going on forever. This is 2 pi time. This is cosine of t. So just a regular old cosine curve, period, is 2 pi. Given the context of this thing spinning around, my angular speed is 1 radian per second. So it takes 2 pi seconds to go all the way around. The slope of this is negative sine, as we just went through. And that would be negative 1 and 1. 1 and negative 1. So this would be negative sine of t. All right, so this is just the simple recap of what we did over there, except omega is equal to 1. Let's do the slope of sine, or the slope of negative sine, I should say. Where is this equal to 0? Where's the slope of this equal to 0?
At the origin. And then everywhere where it crosses the x-intercept.
All right, that's answering the first question I asked, not the second question I asked. The first question was where is it equal to 0, but that was not really what I meant to ask. The question is where is the slope of this equal to 0?
So, peak and valley.
Yeah,
Oh.
peaks and troughs. So there and there. In this first segment here, what can you tell me about the slope?
I'm tempted to say it's decreasing, but you got anything you're saying that, so.
Well, in this case, you could actually get away with it because
It's approaching.
well, actually by what Kano was saying earlier, it's increasing the entire time.
Because it's.
My slope is 0 here. My slope is
Negative something.
negative something. I'm going from negative something to 0, so that's an increase.
So I can't even say it's approaching 0. Well,
It is approaching 0. The question is, it's approaching 0 from which side?
right, because it's, okay.
And I think Zach hit on, what can you tell me about the slope of this first segment?
It's getting less negative.
Okay.
It was negative and then it's moving towards 0.
So it starts out at some negative value and becomes less negative. In this region from here to here, what can you tell me about the slope?
We're increasing for a while.
And then when do we stop increasing?
At the peak, when it trends.
So this slope is bigger than this slope.
No, it starts decreasing before the peak. It's still a positive slope, but it's less positive until
All right.
it's 0.
I will say I was expecting this to go in a different direction, but let me draw it, since we're doing it this way, let me draw this better.
Yeah, I feel like we're making it a lot more complicated than it usually is.
Also, just to clarify, is that a -2 up on the cosine of t graph?
It's a 1, I can't believe you thought it was a 2.
Gosh, must be C.
It was a Z or Z, and Z obviously equals 1.
Right, of course.
Yeah, sorry about that, thank you guys. Hey, I must have been thinking 2 pi or something. Alright. So my slope is becoming less negative, it becomes 0 here. Then it starts to become, then what happens here?
It starts increasing.
Okay, at what point does it start to decrease?
There.
Then it's the intercept. That's when
Yep.
it reaches 0. I'm not, it doesn't reach 0 here, but that's when it starts to.
It starts
Right,
to.
so that's when I'm at a peak maximum. You know, it's a little bit off because I'm doing this from the side. And then what happens in this last bit?
It starts to increase again, but like it's. I'm saying increasing because it's becoming steeper, but it's negative. It's in the negative
Okay.
direction now.
So like that. What is this graph?
Negative cosine.
Yep. So now, let's see if I can draw this better than that. Again, period of 2 pi. This is time. This is negative cosine of t. What does the slope of this look like?
The sine curve.
Yes. It's 0 here, it's 0 here, and 0 here. In this first region, it's positive. So I start at 0, it's positive, I have to end at 0, so basically we're looking at that, and then it's negative, and this is just the sine curve.
Yeah, derivatives.
Yes, yes indeed. Notice the pattern here. We started with cosine, then we went to negative sine, then we went to negative cosine, then we went to sine. Well, after sine, what do you think we're going to get next?
Cosine.
And it just cycles. And as has been mentioned, if this is the initial function, that's first derivative, second derivative, third derivative, fourth derivative, fifth derivative, sixth derivative, seventh derivative, and so on. Or if you start here, first derivative, second derivative, third derivative. Now, if we throw omega into it, well, we've already done the first one. So if I start with cosine of omega t and do the slope, I get negative omega sine omega t. And then if I do the slope of that, what's going to happen? Do it in parts. First off, what is negative sine going to become when we do the slopes?
Negative cosine.
We've got that omega t here. And then every time we do that, whatever is next to the t, we bring that out front. We already have one omega, we get a second one, so this is omega squared. And then next one.
Wait, is. Sorry, go ahead.
That's it to the third.
Okay, so
Negative omega cubed sine of omega t.
notice when we go from negative cosine, the sign goes away. Oh, sorry, the negative sign goes away.
Ah,
So it becomes positive.
right, okay.
You said we bring the omega out to the front, so why is it still next to the t?
It's always going to stay there.
Okay.
It always stays inside there, it's just that it goes through a transporter beam and produces two of them. One is good, one is evil.
One, yeah. So one is like.
The dichotomy of the whatever. I just want to use that word.
You did great.
Thank you.
All right.
The angular sign. That's what I was.
I prefer the explanation calculus. That makes more sense.
Yeah. And again, this is J-Mole.
I do remember us talking about this last semester, but I don't remember what we did with it.
Last semester, when we were dealing with simple harmonic motion, we had a situation where we had acceleration and position were related to each other. So we needed some function for position such that the slope of the slope produced something that was the negative of the position. So we started out with cosine, slope of the slope gets us negative cosine, and then from that we figured out the period of simple harmonic motion. That's what we saw last semester. Or in the first semester course, I should say. And presumably, those who did not have me would have seen it during the simple harmonic motion section. So, if you started with something, going back to the initial Kato's question, if we started with something that started at 0, that means you're probably going to be starting with sine, and then the slope would be a cosine, slope of that would be negative sine, and so on. That's where that would pop in. I will say, doing this now will save us about a half hour next Monday, if you remember this. If you don't remember it, then I guess we didn't save any time.
So just to clarify, you said if something were to start at 0, what is the something that we're talking about that might start at 0?
So in the case of this, if I was trying to describe the motion of this thing as it spins around, if the magnetic flux started at 0, so magnetic field going that way, the flux would be 0 here. And then this would start out with a sine. If I started it pointing this way and spinning it with angular velocity upwards, that would start at 0 and then go negative.
It's a negative sign.
And so, yeah, so we'd be starting with a negative sign.
Right, okay.
If I started here and started spinning it like that, that would be a negative cosine.
Okay.
Or, just redefine one of your directions as positive, and suddenly it becomes positive cosine.
Are we about to do a problem with this? Is that the next, or no?
I was not planning to. I was going to use this.
I would want to use it either way. Yeah, that's what I was looking for.
Yeah.
Figure out some next step. Okay.
Any other questions right now? Since this is the basis of all AC generation, let's do another symbol. This is the symbol for an AC power supply. And if you recall, I know it hasn't been that long, but still, this is the DC power supply.
Oh, like the battery that we talked about.
Absolutely.
Okay, I was looking at T's, I couldn't figure it out. But
Yeah,
I was like, that makes
battery.
sense.
Or for the purists.
That's me. I'm a purist.
There we go.
So.
The only having the one power cell DC power supply or representing batteries was just to torment you.
Ah, good. I figured as such.
Yeah. It's all part of the conspiracy. If your teachers in your other classes or instructors in your other classes are not doing the same thing, then
They're not teaching right.
that's right. Then they reneged on the bargain that we struck up.
Mm-hmm.
So if I have an AC power supply and a resistor here, let's take a look at what's going on, the relationship between the voltage between the two and the current between the two. Kirchhoff's rule still applies. I gain some voltage or I lose some voltage, depends upon, let's just take a snapshot in time. Let's assume I gain some voltage here. I'm going to lose that much voltage at this point. So the change in the voltage across my power supply plus the change in the voltage across my resistor better be 0. This right here is going to be some maximum voltage times either sine or cosine. It all depends on how you want to start it. I guess since we were just doing sine right here, so let's do sine of omega t. Minus 0. Now there's two things that pop up here. One, actually, I'm going to hold off on that for just a second. I'm using a lowercase v here. Tradition is when you're talking about the instantaneous voltage, because the voltage is fluctuating back and forth. If you're talking about the voltage at some particular moment, you use lowercase. And if you're talking about the maximum voltage, you'd use uppercase. So Ohm's law, which is for DC, delta V equals IR, would be, the other habit is they tend to drop the deltas now. 4, 5, 5. Because you don't want to get too comfortable with the same letters. You just want some variation of it.
You said that this is like Ohm's law for AC? Correct?
Yes.
Does that mean that the lowercase I is like the current in that moment, sort of like the lowercase v is the voltage in
Yes.
a particular moment?
At some particular time t. So my formula for this, well, we can actually solve for it right here. In this circuit right here, my voltage is epsilon sine omega t. My current would be, well, epsilon divided by r sine omega t. So if I plotted these three things, we have the voltage from the power supply, which would look something like this. So this is in black here. We'll do the power supply. Voltage for the resistor